Hello everyone, my name is Royer-Rivard and today I'm going to present to you my paper which is called End-to-End Deep Learning Model for Cardiac Cycle Synchronization from Multi-View Angiographic Sequences, which was done during my master at Polytechnique Montréal. First of all, I did this project because heart disease are a serious health issue and coronary angiography, which his procedure is shown by those images, is still widely used today, and the interpretation of the angiograms is not easy because of all the different angles the arteries must be seen to understand the severity of the disease. I want to help cardiologists by creating a real-time dynamic 3D model of the coronary arteries from the angiographic sequences. It would look a bit like this one, plus the time dimension added. That could be helpful in several ways. It could help them choose the optimal views that would reduce the total radiation received by the patient. It could also do an automatic evaluation of the severity of the disease to help them choose the right treatment. And it could also guide them during the intervention that would lead to a reduction of the contrast agent that would be injected into the patient. To create this dynamic 3D model, multiple steps are needed. First, we need to synchronize different views, which is the subject of this paper. We also need an automatic segmentation of the coronary arteries. And from those segmented arteries, we need to match every point from a view to another view. And with these matching, we can then create the 3D reconstruction. The goal of my project is to synchronize different views of the same heart based on the cardiac phases, and this can be done by slowing down one of the two videos. To put you in the context, synchronization is usually done with electrocardiogram gating. This method consists by identifying specific waves in the electrocardiogram signal to keep only the frames that were recorded during those specific period of time. This is a simple solution and it works generally well. However, it absolutely requires the electrocardiogram signals. It also removes the temporal dimension and can be thrown off by artifacts in the electrocardiogram signals. The recent work of Suesdale et al. Made use of deep learning to identify the cardiac phases directly from the pixels. This allowed them to keep the temporal dimension and did not depend on the electrocardiogram signal. However, it required a ton of data to train from their model from scratch. The main inspiration for my article is from a paper of 2017 called Learning Robust Video Synchronization Without Annotations, which synchronizes dashcam footage of the same route taken in different seasons. It does so by extracting feature vector from the images and comparing them from one video to the other. With this comparison, a distance matrix is made and pathfinding is done to find the best synchronization. Here is an overview of the method. First, we extract sequences by taking 3 consecutive images of different views, and then we pass them through our pre-trained and fine-tuned deep convolutional neural network, which outputs a feature vector describing the sequence of 3 images. Then we compare all those feature vectors to create this similarity matrix that compares all the frames of video A and video B. On that similarity matrix, we do pathfinding to find the best temporal correspondence between the two views. My data consists in 271 sequences from 42 pediatric patients, and only the frame with a high gradient are kept. If you can see in this graph, the green portion, the images look like this, where we clearly see the arteries, while the other portions look like this image, where we can't see the arteries. So the video have an average of 55 valid frames, and they are recorded with a frame rate of 15 or 30 frames per second. The images are shrunk down to fit to the neural network, and the input image are monochrome with only one channel. And fortunately enough, the whole dataset fits in the memory, so it simplifies the training process. My model is a deep convolutional neural network pre-trained on ImageNet, and I stack 3 monochrome consecutive images to create one input image, like the model is used to parse. This creates an embedding vector that describes the sequence of 3 images. The ground truth data used to train my model is defined by the electrocardiogram signal captured during the angiography. My algorithm smooths the signal with a Gaussian filter and then identify the R-wave peaks based on the slope and narrowness of the curves. Like I've said before, this kind of algorithm can be thrown off by artifact in the electrocardiogram signal. Once the R peaks are identified, they are aligned from 2 videos like this and linearly interpolated in between. This gives us a matrix that has values of 1 where the R peaks are aligned and a value of 0 when they are out of phase. My model uses a training loss that takes a batch of feature vectors generated from different frames of the same video. For every possible pair, we compute the cosine similarity, which is simply a normalized inner product between the 2 feature vectors. The cosine similarity outputs 1 if the 2 feature vector points in the same direction and -1 if they point in opposite direction. The result is then compared to the ground truth and averaged over the whole batch. This loss function allows the model to learn to generate similar feature vectors for sequence of the same cardiac phase and opposite feature vectors for sequence of different cardiac phases. During training, we tested different models like the EfficientNet, MobileNet, and ResNet, and found out that the best performing one was the EfficientNet B1 with a feature vector size of only 4. Freezing the running variable on batch norm layers also helped a lot. Once the model is trained, it can be used to generate distance matrices by comparing the feature vectors of 2 videos. Every pixel in these distance matrices represents the Euclidean distance between the feature vector of a frame in video A and the feature vector in a frame of video B. As you can see, stripes pattern appear in these distance matrices. These stripes represent the frame pairs where the cardiac cycle are synchronized. To extract those stripes, we use a pathfinding algorithm that would start at every 5 pixels on the left side and top side of the distance matrix. The pathfinding algorithm then goes towards the bottom right and then comes back towards the top left. This allows us to find every stripe in the distance matrix, but only the longest and straightest is kept to evaluate the model. Each point of the selected path is compared to the same point in the ground truth matrix. This gives every point a value between 0 and 1. To rate the whole path, we take the average of every point. And to evaluate the whole model and not a single synchronization, we compute the score for every pair of videos for all patients. As you can see in this cumulative histogram, the bottom 10% of the synchronization scored between 0.65 and 0.85, while the top 10% have a perfect score of 1. The average score of the model is around 0.96. Here are some examples of synchronized video pairs of the same coronary arteries from different angles. As you can see, the cardiac phase are perfectly synchronized. This concludes my presentation. If you have any question, don't hesitate to reach out. Thank you.